Okay, so here we are, lessons 19 and 20. I'm going to combine lessons 19 and 20 together because I didn't get the slides done in time for a live lesson 19, but I've got 20 pretty well sorted out. So I'm just going to make one video to cover both lessons. So the issue is, what's the finite square well and what kind of states does it have, both bound states and scattering states? So what is a finite square well? Well, it's a well with finite depth and width. So you can imagine drawing a picture of such a thing. It might look something like this. We're going to make the potential energy outside the well equal to 0. That's a convention. It's a nice convention because it means particles that escape from the well have no potential energy outside the well, and all their energy is kinetic. But inside the well, there's a negative potential energy, and it has a depth of V0, so the potential energy at the bottom of the well is minus V0. Also, the well has a width of 2a, and we denote that by having the right-hand edge of the well at plus a, and the left-hand edge of the well at minus a. This gives us a symmetric potential, and one of the consequences of being symmetric is that the wave function has to be either symmetric or anti-symmetric. So marching ahead, we've got the Schrödinger equation, our old buddy. We know the wave function has to have a certain symmetry. We also know that the wave function itself has to be continuous at the points where the potential changes, and the first derivative must also be continuous at those points. It's easy to solve the Schrödinger equation in regions of constant potential. It's just depending on whether the kinetic energy, or depending on whether the energy is greater than or less than the potential energy, it'll either be traveling waves, e to the plus and minus ikx, or it'll be real exponentials, e to the plus and minus kappa x. For some reason, Griffiths chooses to use L instead of K as the wave number inside the well. So when you write out the solution, it turns out to look something like this. It's got a cosine Lx instead of Kx inside, and it's got a decreasing exponential in the positive x direction and a decreasing exponential in the negative x direction outside the well. The notation at the bottom just says that it's symmetric, so that if you want to know what the wave function is at -3 or whatever, -62, you plug in psi at plus 62, and then it's equal to that because it's symmetric. Now, there is an anti-symmetric solution where you'd have a sine Lx in the middle and a minus psi of -x in the region for x is less than -a, but basically it's the same idea. I also want to point out that to begin with, I'm going to look for bound states. That means we're looking for states for which the energy is negative. So let's march ahead. We'll move the math up to the top of the page. Let's apply the condition of continuity of the wave function at x equals a. That means that d times the cosine of La is equal to f e to the minus kappa a. We just plugged a in for x in the middle and in the right formula, and demanded that the wave function be equal on either side, whether you evaluate it using the right-hand formula or the left-hand formula. We don't have to worry about applying the boundary condition at minus a because of the symmetry of the wave function, so we won't worry about that. We get the same thing anyway. Then let's apply the derivative boundary condition. The wave function's derivative must also be continuous. That means that if you calculate the derivative of the wave function and then plug in a, either in the middle or on the right-hand side, you have to end up with the same thing. And you'll notice that there's a d in each of these equations and there's an f in each of these equations, and they come in the same way. So if we divide the bottom equation by the top equation, we get a single equation, which is that the wave number times the tangent of La is equal to kappa. So that gives us a constraint on L and kappa. There's another constraint on L and kappa, which I'll describe in a moment. But before I get to that, let's talk about the antisymmetric state. The only difference with the antisymmetric state is it would have a sine in the middle instead of a cosine. And all that does is change the cosine in the continuity equation to a sine, and it changes the negative sign in the derivative continuity into a plus cosine. And if you plug all that in, you find that what you get is L times the cotangent of LA is equal to minus kappa. So this is the condition for the antisymmetric wave function. So we have one condition for the symmetric and a different condition for the antisymmetric case. Okay, marching ahead, let's get back to the issue of the energy. I want to point out that that there's a relationship between L and kappa. The only relationship isn't that these two transcendental equations have to be solved, but L and kappa have a further constraint. And that is that the kinetic energy inside the well has to do with the wavelength of the sinusoidal wave function inside the well, and it's p squared over 2m. Of course, p squared is just h bar L squared. And so you can evaluate the kinetic energy inside the well as h bar L quantity squared divided by 2m. Now, the other thing that's interesting is outside the well, when the energy is less than 0, you get an exponentially decaying wave function. If you compute the kappa, the exponential decay factor outside the well, you'll find that h bar kappa squared over 2m is just the depth of the energy below 0. In other words, it's the magnitude of the energy. And you can see from the picture that the sum of those two has to be nothing other than the depth of the well. So that means that h bar kappa squared over 2m plus h bar L squared over 2m is equal to V0. If I define h bar L0 squared over 2m to be V0, that depth, then I can see that I get a condition on L0, L, and kappa. It looks almost like a Pythagorean theorem. The point is L0 is determined entirely by the depth of the well and the mass of the particle. So if you make little l bigger, you got to make kappa smaller. And if you make kappa bigger, you got to make little l smaller. So that means that high kinetic energy states have a very small kappa, and low kinetic energy states have a very large kappa. Intuitively, what that means is that states where the energy is deep down inside the well, close to the bottom of the well, do not penetrate very far outside the well. But those states that have a high energy close to the edge of the well, close to 0, they have a large little l, and that means their kappa is very small, which means they penetrate deeply into the forbidden zone outside the well. So that's the meaning of that statement. The mathematical consequence is that if you know little l, you also know kappa, so they're not independent of each other. You can use this relationship to relate one to the other, and that's exactly what we're going to do. Griffiths defines z to be little l times a, and he defines z naught to be L0 times a. If I multiply that Pythagorean type equation by a squared, I get a new Pythagorean type equation, except that the first term there is going to be z0 squared, the second term is z squared, and we're going to leave the last term alone. The idea is to use the last term. Anywhere we see that in our equations, we'll replace it by using this Pythagorean-like theorem, or this Pythagorean-like expression, to replace it with something that only depends on z. So we're getting rid of kappa, and we're replacing it with z. We're getting rid of L everywhere, replacing it with z. That's the plan. So let's go back to these two transcendental equations. Let's multiply both sides by a. So now we have a new transcendental equation, except notice that now we have z times the tangent of z is equal to kappa a. But kappa a is the square root of z0 squared minus z squared, using the Pythagorean-like formula from the previous slide. And we can do the same thing with the cotangent version. And so now what we get are two transcendental equations, one for the even states, one for the odd states, that depend only on this z. And of course z is L times a, so if you know the width of the well and you know z, you can figure out little l. You can get the kinetic energy inside, you can get kappa outside, again going back to the Pythagorean theorem or formula or whatever that thing is. And you can see that these transcendental equations look something like this. If I've graphed the square root of z0 squared minus z squared divided by z as that black curve, and then the red and green curves are the tangent and minus the cotangent of z, you can see that for this particular value of z0, I think z0 is 4 in this picture, that there are 3 solutions, and 2 of them are even and 1 of them is odd. And Griffiths basically stops there and goes on to scattering states, but I can't stop there because I think this transcendental equation is pretty hard to get intuitive results from because it's so goofy looking, all the curves that you don't have a hard time drawing. And so I want to point out that there's a much simpler way to do these transcendental equations, and that is to recast them in terms of sines and cosines. So here's the plan. Let's start back at the beginning, and let's square both sides. So we'll square both sides of this equation. Then let's add z squared to both sides, and we get this. And then I want you to remember that tangent squared plus 1 is secant squared, and cotangent squared plus 1 is cosecant squared. So I can substitute cosecant squared and secant squared for those guys. But remember, what is secant squared? It's 1 over cosine squared. And what is cosecant squared? It's 1 over sine squared. So I can solve those guys, take the square root, and I get the absolute value of cosine is z over z0 for the even states. I get the absolute value of sine is z over z0 for the odd states. We have to take care, though, because when we did the squaring and the square rooting, we lost some sign information. That is one drawback of this approach. But it's easy enough to figure out. If you draw the thing, you can see that all you have to do is draw the 0 to 90 degree cosine curve, and then just repeat it every pi over 2. So between pi over 2 and 2 pi over 2, it's sine. Between 2 pi over 2 and 3 pi over 2, it's minus cosine. But it's the same curve. You just repeat it over and over again every pi over 2 radians for z0. And then the z over z0 from the right is just a straight line. It's a straight line that's 1 when z is equal to z0, and it's 0 when z is equal to 0. And even on a bad day, I can draw a straight line. And so you can see in this case, there are, 1, 2, 3, 4, 5, 6 solutions in the case that I've drawn here. But it's easy to extract values of z from this guy. And you don't require great feats of sketching or graphing or Newton's algorithm or any of that business. So that's the point. Of course, z0 is the value of z that corresponds to the full depth of the well. Basically, it's L0 times A, and so you just compute that number. Once you know the depth of the well and the width of the well, you can calculate it. It's just a pure phase, no units. All right. So that's how that works. I want to, here are the solutions. I'll point them out to you. And the other thing I want to point out is if you pick one of those solutions and then you go back and sketch the sinusoid all the way back to the origin, what you have is actually a representation of the actual wave function, because it does correctly predict the slope and the height of the wave function at the edge of the well where it matches up with the exponential part. So we'll get a chance to try that out when we work on Computing Project 6, and we'll also do some sketching exercises in class so you guys get some experience with that. So I wanted to take a few minutes just to show you guys a quick demo of the bound state solutions to the finite square well and how they relate to the interior and exterior solutions and how the boundary condition comes into play. So what I've got here is 2 curves. This is the top curve here. This one, the green curve, is a cosine inside the well. The well has a width or a parameter. Half the width is 1, so I guess it's a well width of 2. And we have a K0 of 5, so that represents the depth of the well. And of course, since A is 1 in whatever units, I guess you could say EV nanometers or whatever you like, then Z0 from Griffith's algebra is also 5. So the way this thing works is I I have a dial here, I can adjust k. So by adjusting k, I get the interior wavelength to go up and down, and then of course you know that kappa and k are related by this Pythagorean-like relationship, and so it means that if I make k big, I make kappa small. So you can see as k gets bigger, the exponential outside the well gets weaker. Okay, so that's kind of the idea. Now the question is, what are the solutions going to be? I've got another graph here I can show you that is the one we cooked up in class to find the k values, or really the z values, that satisfy the boundary conditions. And you'll notice that in this case, I have set, well, I guess z0 is adjustable, so I can adjust z0 to whatever you like. I'm going to set it to 5 here, and there's some kind of quirk that, well, anyway, I set z0 to 5, so when z is equal to 5, z over z0 is equal to 1. You can see here's the 1, and there's z0 is equal to 5, and there are 4 solutions. So it looks like the first solution is right about here, which, if I'm reading correctly, is about 1.3 or so, 1.3. So if I pop back over to this side and I dial the k value to 1.3, you'll notice that that's exactly the point where the kink in the slope between the cosine in the inside and the exponential on the outside, that kink disappears. So 1.3 is the value of k that not only satisfies the continuity. Notice I got this thing set up so the continuity is always there, but the derivative has a kink in it except at certain special values of k, and those values of k are the ones that solve the transcendental equation. Let's check the next one. It looks like that's at about 2.6 or so. Now, one other thing I want to point out before we move on, and notice how sharp this exponential is. It goes to 0 very quickly. It's down in the dirt by 1.6. But let's march ahead and let's find the point where the other solution, the asymmetric solution, and notice it's right about 2.6. The kink goes away at 2.6, but the exponential now is a little bit weaker. It's not coming to 0 quite as quickly, but that value of k, 2.6, is right about where the slope and the continuity boundary conditions are both satisfied. Now, where's the next one? It looks like it's going to be about 3.85 or 3.9, I guess 3.80 something. That's kind of hard to see. Let's go ahead and dial this up to 3.80 something, and notice that that's right about where the kink disappears in the cosine solution, in the symmetric solution. So each solution to this transcendental equation corresponds to a k value where the continuity equation and the slope condition, the derivative of the wave function, are continuous at the well boundary. And notice that each one corresponds only to a solution for a particular symmetry, even, odd, even. And here we see that the last solution looks like it's going to be right around 4.9 or so, almost 5, not quite, 4.9. Let's dial that in. And this is going to be an antisymmetric solution. Let's go ahead and dial it up, 4.9. There it is. And notice we've got a nice continuity in both the wave function and the derivative, but notice what's happened to kappa. Kappa is so weak now, the particle is reasonably expected to be out here at 3 and 4. You could measure it out here at 4, and that means that the energy is so high, the thing's about to escape the well, and the exponential stretches way out into the forbidden zone, into the classically forbidden zone. So anyway, that's what I wanted to show you guys. I hope that that helps your intuition about how this stuff works. All right, let's move on to scattering states. Scattering states, of course, are just states where the energy is positive. In this case, we're going to talk about waves that come in from the left, so the left-hand wave function might look like this. I'm using an A amplitude of 1. The idea is that these other coefficients, B, C, D, and so on, are all proportional to A. So we can think of B, if I set A equal to 1, I can think of B as being the amplitude per unit of incoming amplitude that gets reflected. And in the middle, I can think of C as the amplitude that passes through to the middle, and D is the amplitude that gets reflected back into the middle. And finally, F is the amplitude that passes completely through the well for a scattering state. Again, it's per unit incoming amplitude. So if I double the incoming amplitude, I'd get 2F, and if I tripled, I'd get 3F, and so on. But the advantage of that, of course, is when it comes to calculating the reflection coefficient, the probability of reflection. Normally, we would have to take B divided by A, magnitude squared, but A is 1. I've forced it to be 1, so I end up with a reflection probability that's just the magnitude of B squared. So dividing by 1, of course, doesn't change it. So how do we solve the problem? We apply the boundary conditions at x equals plus a and x is minus a, and we solve the 4 equations. Notice there's 4 equations and 4 unknowns. That's the idea. It's rather tedious. Griffith does it so you can see how it's done. But I want to point out that in practical work, it's easier to use a computer. So I just want to point out that you can use matrices in a computer to solve this problem. You've got the left, middle, the left and right-hand boundary conditions. I didn't really want to jump quite that far. Okay, you got the left and middle boundary condition and the middle and right boundary condition on the continuity of the wave function and the continuity of the first derivative. So that gives you 4 equations, but we have 4 coefficients, so we ought to be in good shape. So let's apply these boundary conditions one at a time. The wave function has to be continuous at the left side of the well. That implies that this must be true. We just plug in negative a for x in the wave function on the left and the wave function in the middle. Then we do the same thing with the derivative on the left, and we get this condition. Then we apply continuity to the wave function on the right. We get this condition. Notice also, I forgot to say it, but there's no incoming wave on the right. There's only an outgoing wave on the right, and that's consistent with particles being thrown at the well from the left with an amplitude of 1. And finally, we apply the derivative boundary condition on the right, and that gives us that condition. So we've got 4 conditions, and we've got 4 unknown coefficients, B, C, D, and F. Now the idea here is to move all the constant coefficient terms to the right, leave all the constant terms with no coefficients to the left, and we get 4 equations that you can recast as a matrix multiply. So the idea is you think of the constants on the left as a vector, you think of the functions that you multiply the coefficients by as a matrix, and then of course the vector of unknown coefficients b, c, d, and f shows up as a vector on the right. How do you solve that problem? Well, linear algebra dictates what you do is you take the inverse of the matrix and you multiply both sides with its inverse, and out should come the unknown coefficients. Of course, you know everything. If you know the width of the well and you know the depth of the well, that means you know A, you know kappa, you know K, and of course I used K here for the free waves, and you can calculate the result. Here's the little Python program that does exactly that. I loop through a series of energy values. I calculate the K for the incoming wave. I calculate kappa for the wave inside the well. Now it turns out because V is complex, kappa can turn out to be either a real or an imaginary number. So if the energy is greater than the potential, then you end up with a real kappa. I'm sorry, an imaginary kappa, which gives you a traveling wave, and if the energy is lower than V, then you get a decaying exponential inside the well. If V is negative, that means you always get for any incoming wave would have a positive kinetic energy, you'd end up with a traveling wave inside. Anyway, the point is you create this M array, and notice that because everything is complex, you can spell it just the way It's written mathematically, and then you define the constant vector, the B array, and then you just use the linear algebra operators, take the inverse, multiply by B, and then pluck out the coefficient you're interested in. In this case, I was plucking out the transmission coefficient and calculate its magnitude squared, and then make a list of the reflection coefficient as a function of energy, and out comes a graph. It looks just like the graph from Griffiths. It's the transmission coefficient, the transmission probability, as a function of energy. Notice that if the energy is too low, then you don't get anything through, but if you have an energy that's high enough, you get a probability of transmission goes up. There are certain energies that have just the right characteristic where the transmission probability goes to 1. Those are so-called resonant energies, and if I kept graphing to higher and higher energy, you'd reach a point where everything gets through no matter what its energy, and that kind of makes sense intuitively. All right, very good. So that's the idea. We will use this idea of calculating transmission coefficients using matrices in Computing Project 7. I already told you a little bit about Computing Project 7 in the when we discussed scattering states of the Dirac delta function potential, but we'll run into that again soon enough. I hope that helps, and we'll talk to you soon.